To search for alien life, astronomers will look for clues in the atmospheres of distant planets, and the James Webb Space Telescope just proved it's possible to do that. This is by Chris Impey, University Distinguished Professor of Astronomy, University of Arizona, and Daniel Apai, Professor of Astronomy, Planetary Sciences at University of Arizona. This is on The Conversation. The ingredients for life are spread throughout the universe. While Earth is the only known place in the universe with life, detecting life beyond Earth is a major goal of modern astronomy and planetary science. Obviously, they're looking for a Goldilocks zone Earth-like planet where it would be much easier to set up a human space station or colony. Now, they say, two scientists who study exoplanets and astrobiology, thanks in large part to next-generation telescopes like James Webb. We know that it's different from the others because it takes images by infrared, so it could see things in the dark. So researchers like us, they said, will soon be able to measure the chemical makeup of atmospheres of planets around other stars. The hope is that one or more of these planets will have a chemical signature of life. Habitable exoplanets. Life might exist in the solar system where there is liquid water, like the subsurface aquifers on Mars, or in the oceans of Jupiter's moon Europa. However, searching for life in these places is incredibly difficult, as they're hard to reach, and detecting life would require sending a probe to return physical samples. Now, of course, that is also dangerous itself, because we don't know what those samples will contain and how they could contaminate our Earth. Now, many astronomers, they said, believe there's a good chance that life exists on planets orbiting other stars, and it's possible that's where life will first be found. Theoretical calculations suggest that there are around 300 million potentially habitable planets in the Milky Way galaxy. Yes, in our galaxy, 300 million habitable planets. In our galaxy alone, and several habitable Earth-sized planets within only 30 light years from Earth, essentially humanity's galactic neighbors. So far, astronomers have discovered over 5,000 exoplanets, including hundreds of potentially habitable ones, using indirect methods that measure how a planet affects its nearby star. These measurements can give astronomers information on the mass and size of an exoplanet, but not much else. Looking for biosignatures. To detect life on a distant planet, astrobiologists will study starlight that has interacted with planet's surface or atmosphere. If the atmosphere or surface was transformed by light, the light may carry a clue called a biosignature. For the first half of its existence, Earth sported an atmosphere without oxygen. Okay, so our Earth was also as small as our moon, because our Earth is expanding, but it didn't even have oxygen. The first half of the existence, even though it hosted simple single-cell life. Earth's biosignature was very faint during this early era. That changed abruptly 2.4 billion years ago, when a new family of algae evolved, and the algae used a process of photosynthesis that produced free oxygen. Oxygen that is not chemically bonded to any other element. And from that time on, Earth's oxygen-filled atmosphere has left a strong and easily detectable biosignature on light that passes through it. When light bounces off the surface of a material or passes through a gas, certain wavelengths of the light are more likely to remain trapped in the gas or material surface than others. This selective trapping of wavelengths of light is why objects are different colors. Leaves are green because chlorophyll is particularly good at absorbing light in the red and blue wavelengths. As light hits a leaf, the red and blue wavelengths are absorbed, leaving mostly green light to bounce back into our eyes. The pattern of missing light is determined by the specific composition of the material the light interacts with. Because of this, astronomers can learn something about the composition of an exoplanet's atmosphere or surface by, in essence, measuring the specific color of light that comes from a planet. This method can be used to recognize the presence of certain atmospheric gases that are associated with life, such as oxygen or methane, because these gases leave very specific signatures in light. It could also be used to detect peculiar colors on the surface of a planet. On Earth, for example, the chlorophyll and other pigments plants and algae use for photosynthesis capture specific wavelengths of light. And these pigments produce characteristic colors that can be detected by using a sensitive infrared camera. If you were to see this color reflecting off the surface of a distant planet, it would potentially signify the presence of chlorophyll. Telescopes in space and on Earth. It takes an incredibly powerful telescope to detect these subtle changes to the light coming from a potentially habitable exoplanet. For now, the only telescope capable of such a feat is the new James Webb Space Telescope. As it began since operations July 2022, James Webb took a reading of the spectrum of the gas giant exoplanet WASP 96b. The spectrum showed the presence of water and clouds, but a planet as large and hot as WASP 96b is unlikely to host life. However, this early data shows that James Webb is capable of detecting faint chemical signatures in light coming from exoplanets. In the coming months, Webb is set to turn its mirrors towards Trappist 1e, a potentially habitable Earth-sized planet a mere 39 light-years from Earth. Webb can look for biosignatures by studying planets as they pass in front of their host stars and capturing starlight that filters through the planet's atmosphere. But Webb is not designed to search for life, so the telescope is only able to scrutinize a few of the nearest potentially habitable worlds. It also can only detect changes to atmospheric levels of carbon dioxide, methane, and water vapor. While certain combinations of these gases may suggest life, Webb is not able to detect the presence of unbonded oxygen, which is the strongest signal for life. Leading concepts for future, even more powerful space telescopes include plans to block the bright light of a planet's host star to reveal starlight reflecting back from the planet. This idea is similar to using your hand to block sunlight to better see something in the distance. Further, space telescopes could use small internal masks or large external umbrella-like spacecraft to do this. Once the starlight is blocked, it becomes much easier to study light bouncing off a planet. There are also 3 enormous ground-based telescopes currently under construction that will be able to search for biosignatures. The giant Magellan Telescope, the 30-meter telescope, and the European Extremely Large Telescope. Each is far more powerful than existing telescopes on Earth, and despite the handicap of Earth's atmosphere distorting starlight, these telescopes might be able to probe the atmospheres of the closest worlds for oxygen. Is it biology or geology? Even using the most powerful telescopes of the coming decades, astrobiologists will only be able to detect strong biosignatures produced by worlds that have been completely transformed by life. Unfortunately, most gases released by extraterrestrial life can also be produced by non-biological processes. Cows and volcanoes both release methane, for example. Photosynthesis produces oxygen, but sunlight does too, when it splits water molecules into oxygen and hydrogen. There is a good chance astronomers will detect some false positives when looking for distant life. To help rule out false positives, astronomers would need to understand a planet of interest well enough to understand whether its geologic or atmospheric processes could mimic a biosignature. The next generation of exoplanet studies has the potential to pass the bar of the extraordinary evidence needed to prove the existence of life. The first data released from James Webb Space Telescope gives us a sense of the exciting progress that's coming soon. And this is by Chris Impey and Daniel Apai, University of Arizona, astrobiologists, and it's on the Conversation Creative Commons. Please leave your comments and thank you for your support. Kindly support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.